Hello everyone, I'm Duygu. I'm a postdoctoral researcher at University of Rennes 1 at Medicines Lab. I work with Dr. Jena. And today I will be talking about how we can complement surgeons with situation awareness using computer vision and machine learning techniques. First, a little bit about me. I'm from Turkey. Okay, they tell me to put this closer. So I'm from Turkey, where we drink the most tea in the world. And I did my master's and PhD at State University of New York at Buffalo, which is near Niagara Falls. And if you wonder the climate, this is live footage of some football game being played. And this is the stadium, so it snows a lot there. And I did my master's with my Fulbright scholarship. And I also worked as a research assistant and also project coordinator at Roosevelt Park Cancer Institute. And as you know, the recent advances in machine learning, particularly deep learning, has led to some human-like performance with some particular tasks that requires perception, such as object detection or natural language processing. And we now even have fully automated software that can, for example, detect a tumor in your lung CT, or it can tell you whether you have diabetic retinopathy by looking at the eye imaging. And these are software that use machine learning and computer vision, and they are approved by the government to be used in clinical setting. So while we see these advances in medical imaging, we don't yet see those in surgical domain because we have some unique challenges such as the unstructured environment and also the subjective practices of the surgeons. So in the past, I think Pierre has mentioned a little about this. In the past, the surgical experience was dependent on just one person, the head surgeon, or a very small surgical team. And they had limited tools, and they had limited domain knowledge, and they had limited experience, so they couldn't compare. But today, we are surrounded with many technical advances in the operating room. And we have access to domain knowledge, which is now much broader. And we have access to case knowledge, so we can take our patient and compare it to other cases, similar cases, and we can see what was done and what was the outcome. And we can access a lot of data about the patient himself or herself, and we can monitor their vital signs by many little screens, actually, and many technological devices in the operating room. But it turns out that humans are limited when it comes to cognition, and they cannot really make sense of this data, especially when it is coming from different sources. So it turns out that this is called the information gap. And like I mentioned, we cannot make sense of the underlying patterns and correlations. And this actually leads to information overload, which leads to cognitive overload. And it might, in fact, decrease the capability of surgeons to attend, process, and integrate information efficiently. So it might make them more prone to making medical errors. And as a matter of fact, medical errors are the third leading cause of death in the United States alone. And what is more shocking is that a pilot study shows that 75% of these medical errors goes unnoticed by the team at the time of surgery. So this means that they were able to tell something was wrong only when they look back to their recordings with the videos. So it turns out humans make mistakes not because they are bad at decision making, but because they fail to read vital signs. So for example, according to the study of aviation by Micah Ensley, as much as 88% of human error is due to problems with situation awareness. So it means that they fail to read vital signs, they fail to read situations, which leads to errors. So what is situation awareness then? So Micah Ensley defines situation awareness as the perception of elements in the environment within a volume of time and space, the comprehension of their meaning, and the projection of their status in the near future. So if we are talking about a situation-aware system, ideally we should be first able to perceive our environment. That is, we need to detect the certain key elements such as the objects and actors. And next, we should also be able to put more context to it. We should have more comprehension. So we should be able to refer relationships between actors and objects, for example. And then, again, we should also be able to make projection in the future. We should be able to predict how the situation will evolve. So based on all of these information, we make decisions and we perform the actions. Then we use the outcome as another input knowledge that feedbacks in the system. So I talk about perception, and I mentioned that it is more about cue detection, simple recognition of actors, objects, events. And so you can actually think of this as the object detection problem in computer vision, for example. So we have these algorithms that we use in computer vision using machine learning that can detect and classify objects in a given image. And we would also like to have more context. So by going our example, we don't only want to be able to say that there is a cake, there is a three kids, there are 4 candles in this image, but we actually want to be able to infer that this is a birthday party. And the kid in the orange t-shirt is the birthday boy, and he's turning 4. And the kids next to him might be his siblings or friends. So we should be able to refer more relationships, and we should be understanding the environment better. So again, going with our example, we should also be able to tell what will happen next. So by looking at this image, we can predict that the kid is going to blow the candles, and the other kids will cheer up. And we might actually make a mental note to keep an eye on the birthday boy when he gets near to the candle flame. So then, what do the operating rooms of the future look like by all this situation awareness that we talked about? I will now show you a video as a showcase. In case you don't know, it's from Catch Me If You Can. And, okay, maybe I should first introduce. There's Frank. He's a high school student who is too smart for his own good, but he's a con man. So long story short, he puts on a jacket and goes into the hospital, and this is what happened next. And I hope you will be able to hear.
Oh, in here, Dr. Connors.
Gentlemen, what seems to be the problem?
Bicycle accident. Fractured tibia about 5 inches below patella.
As you can tell, he has no idea what he's doing.
Dr. Harris,
Yes?
do you concur
Concur with what, sir?
with what Dr. Ashland just said? Do you concur?
Well, it was a bicycle accident. The boy told us.
So you concur?
Concur?
I think we should take an x-ray, then stitch him up and put him in a walking cast.
Very good, Dr. Ashland, very good. Well, you don't seem to have much need for me. Carry on.
So what we would ideally like to have is like these 2 gentlemen. So they are able to read the situation, they are able to make a diagnosis, and they are able to give you suggestions on what to do next. And even when you ask them, they are able to justify their reasons. So these 2 gentlemen would put us somewhere around level 4 in this chart, and it shows the different levels of automation in surgical applications, but actually it could be applied to anything that relates to autonomy. But today we will be talking about level 1, where the surgeon is in control, but there's some guided assistance given to him by the automated system, which we believe is a necessary step towards full automation. So I mentioned the problem of perception, and I likened it to the computer vision problem here, like the object detection problem. And so this is what I did basically with my studies, and this is what we do in the lab that relates to computer vision and machine learning. So we reduced the problem of situation awareness in the operating room to a set of problems of computer vision and machine learning. So these are more core problems. So first things first, I prepared this data set, which is called Atlassian dataset. So I was working at Roosevelt Park, and it has video of surgeons in training while they are performing on this plastic set. And it has the annotations of robotic tools, the timestamps of the actions, and the surgeon expertise levels. If you would like to use it, it's publicly available. And first, we wanted to focus on the tools because those are the most informative in the operating field. So that we can also use these to refer to the actions of the surgeons, so we can use it later to put in more context. So we use the subset of this data set. And so this is an overview of our model. As you can see, it's a multimodal input and joint learning model. We learn 2 tasks, so it's a multitask architecture. So we have the inputs of RGB images from the videos that we extract, and we also have the optical flow. That is the RGB representation of the optical flow that we compute between 2 sequence frames. So this tells us about the motion, the small motion that happens between the frames. So we have an architecture that's similar to AlexNet, so it's a simple architecture. And if you are familiar with faster RCNN, we have a region proposal network. So what this region proposal network does is it suggests some regions as an object candidate. And so we don't have to go in a sliding window fashion. So we have these proposals to work with, and we have little anchors that relates its position in relation to its size and scale and the place. So I don't know how much in detail I should go, but I will stop here. So this way we don't have to go in a sliding window fashion, and this decreases the computation time quite a lot. And another thing that helps is that in this architecture, we first convolve the image, and then we work on the feature map that we gather. So we don't have to convolve every time we run a sliding window. So this actually decreases the time quite a bit. And at this time, it was the first to apply deep learning to this kind of problem. So these are some results that we received with our approach. So, and these are some visual results. As you can see, it does a good job, even when, for example, the tool is almost out of sight or it is occluded. And next, we focus on the action. So in our previous example, the architecture, we were using frames. But if we are talking about action, we need to be able to understand the temporal dynamics better. So, for example, using this sequence of images, if we look at the first image only, or if you look at the last image only, it's hard to tell what is happening. But if we have the whole sequence, we can see what is happening very clearly. So this is the idea. We use sequences, so we use the temporal dynamics and changes. So for this one, we use the Jigsaw's dataset. So this is a very popular dataset in our field by Johns Hopkins. And again, the surgeons are trained here in these videos. and they perform 3 tasks of suturing, needle passing, and knot tying. And what is good about this data set is that they have annotations down to the level of small gestures, which are very small activity segments. So while we were trying to detect the actions, our focus was finding common segments of actions, the very small actions. So before this, the conventional way was to just train a model based on the actions that take place under just one task. And they trained another model on another task. But here we focus on finding the common actions. For example, like positioning the needle, it might take place in the first task or the last one, the suturing. And they seem to be very signature when you look at the motion. But of course, the background changes. But we wanted to be able to find these even if they took place in another setting. So this is the overview of this architecture that we use, which is similar to the first one, if you noticed. And so we have, again, a multimodal architecture, multitasking architecture. And we use the flow, like the motion cues, and we use the visual cues of RGBs, again, as input. But here we also have LSTM, which makes use of the temporal dynamics. So we use the LSTM for the sequence inputs, and we use the features that we gather from the CNN part. So here we learn jointly 2 tasks, which is the high-level task, and the gestures that I mentioned, such as positioning the needle. So using these joint relationships, we are able to perform better because we learn, make use of test-specific and shared representations. So these are the results that we achieved, but they seem kind of low on the lower side. But as I mentioned, we are focusing on finding the common actions. So actually, we perform better than the other conventional methods. So up until this point, we were just doing classification. So we reduced the problem of shared awareness to some core problems in computer vision and machine learning. But then there's this problem of how we can put more context to it. So this is where the comprehension comes. So for this, we make use of surgical process modeling and ontologies. So the surgical process modeling aims to define surgeries through the quantitative analysis. So it breaks it down into different levels, hierarchical levels of activities. So what is good about this is that now we have the power of computation because we have computable process models, and we can make use of these models to put our classifications in context. So for example, here we can observe a surgery and come up with a surgical process modeling of just one surgery. And we can also observe more surgeries, and we can come up with a more generic model. And for example, just by using these, we can compare the individual one and the generic one to see how it deviates from the common practice. And we can also couple this with our classification methods, and so we can use recognition and analysis. And for example, here we see a work in our lab by Arno. So we are able to tell that these surgeons are performing the same action, even if their little gestures and little movements tend to differ. So we are able to tell that this is the same action that is taking place. So we wouldn't be able to tell this just by using the classification because of the small movements that differ. And we can also have more context. We know what happens before and what will happen next. We have at least a probabilistic model that we can use. So we also need ontologies because we need a common vocabulary to define these surgical process models. And ontologies are good because they are provide us machine interpretable definitions of basic concepts in this domain. And there's the OntoSPM if you would like to check and help develop. And you can find it on our website. So as I mentioned, the surgical process model breaks down the surgical activities at different hierarchical levels. So we can define these with ontologies down to the level of just one action. So we can represent just one small action using a triplet of verb, instrument, and object, which is usually the anatomical structure that is performed on. And so putting all this together, we now try to put more context to our solutions. So this is another work that we do with University of Tokyo. It's again similar to the previous models, but here we use more modalities of kinematics as well, and we try to solve the problem of having more context with our classification. And this is the other project that we are working on. It's called Condor, and it has many aspects to it. So, so we work with the dataset Collect80, which is again a public dataset, and there will be a newer version of it. So they provide the phases, steps, and action triplets that, like I mentioned, and so it will be extended. So there will be more additions, but I'm not getting into that either. So we can actually work on a new procedure and create an ontology on it by adding things that are more unique to these procedures. So this is what we did when we created a new ontology for it. And okay, this was a video, but it's not working. Okay, so this is the side that University of Strasbourg is more focusing on. So if you could see, this was a video of detection of action triplets in action. And here in Rennes, we focus more on detection of events, which might be medical events or technical events. The medical events could be bleeding, so we would like to warn the surgeon when there is bleeding because they might be missing it. And there's also the technical events that might affect the view. So we want to be able to tell when there is some occlusion that degrades the view, because this is important. It's actually a predictor of the quality of the surgery. So these are the things that we are working on, and thank you for listening. And if you have any questions, you can ask. No questions, I think. Thank you for listening.